Welcome to lecture 29 on risk management and insurance. In this lecture, we will use the Black-Scholes differential equation to determine the value of a European call option or a non-dividend paying stock. We take the European call option, that's one that we can exercise only at the time when the option expires, at the time big T. In an American option, you only can exercise the option earlier. And to make it simple, we take a non-dividend paying stock. So in the last lecture, we had the Black-Scholes differential equation. It's a differential equation. It determines the time pass of the security. But to solve this differential equation, you need an endpoint condition. In finance, it's also called boundary conditions. Each different derivative will impose different endpoint conditions. So endpoint condition for a European call option is this here. If the option is in the money, so if let's say the share price exceeds the strike price of the option, then naturally you exercise and you get the difference. You may have an immediate positive payoff. If the share price is below the strike price, then you will not exercise your option. You just walk away, the payoff will be zero. That's the end point. That happens at the time big T when the option expires. Now you can now use this boundary condition, this endpoint condition, and solve the Black-Scholes differential equation. It's shown how it's done in the Hull book, chapter 15 in the appendix, and it's actually quite easy. So to do it. So maybe have a look at it. So the result is this. That's the solution. It looks quite a complicated solution, but it's really quite easy to solve it and to get this. Now that's this famous equation for the European call option, for the price of a European call option, for the value of a European call option that every finance student knows. So the price of the call option is here the share price, the underlying share price, and you multiply here by the cumulative normal distribution, by the value of the cumulative function value of the cumulative normal distribution up to the point D1, and the D1 you calculate here. And then here you have the strike price, you have E to the power with the interest rate in it, and again here you have the function value of the cumulative normal distribution, now here calculated up to D2. So this has been calculated. That's a solution of the Black-Scholes differential equation for a European call option where the boundary condition is given here in equation 28. When at time big T, let's say the share price is 120 and the strike price is 100 in the option, then naturally you will exercise and you have a payoff of 20. And if at time big T, the share price is only 80 and the strike price is 100, then naturally you don't exercise. You will not exercise the right to buy at 100 if in the market it's only 80. So you give up the option and you just walk away. The payoff is zero. Now, the cumulative normal distribution I have on the next page. You naturally know this. Down here, I have the probability density function. I do it here for a normal distribution. And then the cumulative normal distribution I have up here. It just gives you the probability up to a certain point D1 here. Here's a probability let's say, is about 74% up to this point. And so this ranges here from 0 up to 1. That's naturally something that's well known. So you calculate this D1 value. So you calculate this D1 value. You put it into the cumulative normal distribution. You get the function value of the cumulative normal distribution. So you have the D1 here. You get the function value of the cumulative normal distribution, maybe 0.74 here. And so you plug in here the 0.74. And then you multiply by the share price times small t. And you do it also here, and then you get the option price at the value of that option at time small t. It's very easily done. That's naturally why this formula is so popular. So the option price or the value of the option moves with the current price of the underlying stock S and time t. And the interest rate and the standard deviation here, the volatility of the share price, are treated as constants. So here we have actually only a single parameter in it, which is here this volatility, which comes from the geometric Brownian motion of the underlying share price. That's a scaling factor. That was a scaling factor, the geometric Brownian motion. That's the only parameter. It's also here and here. So that determines D1 and D2, and then you get here those values of the cumulative normal distributions. ST is observed. That's just the current share price of the underlying share at time small t. X is written in the option contract. That's the delivery price. The interest rate, you can also observe, that's the interest rate in the market. And then actually the time until maturity, you also know. So there's only a single parameter, that's this sigma here, which comes from the geometric Brownian motion, which is the volatility of the underlying share. So people were quite excited that they actually can explain the value of an option just using a single parameter, the volatility of the underlying share, which that's what you have in the geometric Brownian motion. So that's treated as constant. But naturally, during a financial crisis, that's not constant, this sigma. And so during a financial crisis, the writers of the option may actually make large profits or loss when this volatility here changes. So that's the entire problem here that we have in the financial markets. We can calculate the option prices, but it's based on the assumption of a geometric Brownian motion of the underlying shares, else this Black-Scholes model does not hold. And it's based that this volatility here is a constant parameter. If it changes, then also the value of the options will change in the market. And that can happen during financial crisis. This volatility, you don't know what it's in the future. Basically, you just take an average of volatilities over the past few days, and then you plug that into the formula. So it's based on historical values. And that's naturally can be questionable, particularly during a financial crisis when this parameter may change. But still, it's quite an achievement. We can explain option prices just using a single parameter. Now, let's discuss this a bit. Does the formula make sense? As I said, you should you should read the proof. How do you derive it? You should read it in the whole book, in the appendix to that chapter. But we can also look at the form and just think a little bit about it. Does it make sense? Now let's assume the call option gets strongly into the money, which means the share price of the underlying stock rises high above the strike price of the option. So it looks now actually good for the holder of the option. The holder of the option, of this call option, has locked in a strike price of X, and now the share price rises in the market, but the holder still can buy it here at this locked in lower price. Now, if S increases very much, then T1 and T2 go to infinity. So if S increases very much relative to X, then the logarithm of it just rises and rises, and so T1 will rise and rise. And same thing here for T2. T1 and T2 go to infinity, and if T1 and T2 go to infinity here, okay, to the right, so naturally here, this value here moves toward 1 of the cumulative normal distribution. So what you do, you can plug in 1 here, and you plug in 1 here. So if it's strongly in the money, put in 1 here, and then the formula becomes easier. So if you put in 1, and you put in 1, and what you have here is actually now the formula of the value of a forward contract, which I gave you in chapter 1. In chapter 1, we use here a small f, and then we had here the value of a forward contract. Don't confuse it with the big F, the forward price. So I discuss here now the value of the contract, the value of an option. So a call option that is strongly in the money is likely to be exercised. It looks good for you. And so it's similar to a forward contract. Because of forward contract, you must exercise. Actually, there you cannot walk out. And here, it's just very likely. It becomes more and more likely that you will exercise. So in both situations, you exercise. With a forward contract, you're just required to exercise it. And so it's the same formula as in chapter 1. So it makes sense. The solution here makes sense. This becomes the formula for the forward contract if really S rises very much above X. Then, okay, it's very likely that we exercise, and the forward contract we must exercise. So it really amounts to the same thing. Now, let's look whether the Black-Scholes solution is consistent with the boundary condition. Naturally, it should lead to the boundary condition at time big T, because we use the boundary condition to solve the Black-Scholes differential equation. So here at time big T, the option expires. Here at time small t, here we calculate the option price, the value of that contract. And at time big T, really we should get the Black-Scholes equation should imply the boundary condition, because we used that boundary condition really to derive the Black-Scholes solution. So here we should actually have this here. So if the share price is bigger than X at time big T, then that's nice, okay? You have to pay X, but the share price is bigger, so you have this positive payoff. If at time big T the share price is less, then okay, you just walk away from that option, the payoff is 0. So let's assume at time big T, the option is in the money. The share price is bigger than X. In that case, as this time moves toward big T, the interval becomes smaller and smaller. So now the T1 and T2 move again toward plus infinity. Let's look at that. So D1, the S is now bigger by assumption at time big T. We look now at time big T, we apply this formula to time big T. So S is bigger than X, so I have a positive number here. So logarithm is a positive number because this here is bigger than 1. And so I'm getting a positive number. Now if T, small t now goes toward big T, that approaches 0. So we divide by smaller and smaller. And so D1 approaches infinity. Also here, we have a number that's bigger than 1, S bigger than X. So the logarithm bigger than 1, that's a positive number. Here again, the denominator starts to approach 0 because time approaches toward big T. And so we have a positive divided by a smaller and smaller denominator. And so again, we get here plus infinity. This approaches plus infinity. And so we have the same situation as before. If this goes to infinity, then up here, the value of the cumulative normal distribution goes up to 1. So we can again plug in 1. Let's again plug in 1. And actually there is an additional step here. You see, this goes to 1, this goes to 1, but then the small t goes to the big T. The time interval gets smaller and smaller, so we get here a 0 power. So this e to the 0 power also goes to the 1. And so we just get s minus x. We just get s minus x. So the value of a call option that's in the money equals s minus x at time big T. And that's naturally exactly what you have here in the boundary condition. If you have a positive value here, maximum, then the value of the call option should be s minus x. That's also what the formula shows. Now let's assume at time big T, it's out of the money. So at time big T, the share price is less than X. So you have the right to buy at 100 in the market, maybe you get it at 80. Okay, so you just abandon the option and the payout will be 0. Let's see whether the formula really shows that. Actually, it does. So t goes to infinity implies now that t1 and t2 go to minus infinity if s is smaller than x. You see, if st is smaller than x, then I have here a number which is less than 1. It's between 0 and 1. And taking the logarithm between 0 and 1 gives you a negative figure. Just remember how the logarithmic function looks. It runs through point 1 on the lower axis. If you are below 1, if you are 0 and 1, then that's negative, and the then that's a number less than 1, and the logarithm of it will be a negative number. And then you divide here again by smaller and smaller. And so this approach is now minus infinity. And same thing here. But just remember here how the logarithmic function looks. So the logarithmic function is something like that, and it goes here to the 0.1. So I have here x, I have here ln x. So if you are below 1, if you are here, then you get a negative value when you take the logarithm. If you are above 1, then you get positive values. So if the option is out of the money, if it's out of the money, so if s is less than x, then that's less than 1, and so we get here the logarithm will be a negative number. And if this negative number you divide by now something that gets smaller and smaller as time moves toward infinity, you get this approach is now minus infinity, and the same thing here. And if it approaches minus infinity d1, then here the value of the cumulative normal distribution approaches 0. So we can plug in for this 0. So plug in 0 here, plug in 0 here, and so the value of the option, if the option is out of the money, is 0. That's what we have here. So the value of the option is 0. So really the boundary condition does hold. The Black-Scholes equation, the solution of the Black-Scholes model implies the boundary condition naturally, because we use the boundary condition to solve the Black-Scholes differential equation. So we have, in the end, we have this boundary condition that it's either a positive payoff or a 0 payoff. So this at time big T just becomes the value of the option at time big T, at the boundary. Remember, we started here in 28, we started with the boundary condition. Okay, so also this, it makes sense. So I have here looked what happens if the option gets strongly into the money, then it's very likely that it will be exercised. Now with a forward contract, it must be exercised, but that's exercise is exercise, so that's the same. So the option just becomes a forward contract. And if at the end at time big T, here at the boundary, at the end, it's strongly in the money, then we have this positive payoff. We are entitled to get the share at X. It's if ST is bigger than X, then we just have this positive payoff. So we have this maximum here. And if at time big T, it's out of the money, then we don't exercise. Naturally, we don't buy at 100 if in the market we get it maybe at 80 cheaper at time big T. So it's out of the money. The option is valueless. And that's exactly what the Black-Scholes solution also shows. Okay, that's so the formula, it looks quite complicated, but one can really discuss it along those lines, okay, whether it makes sense. And so naturally, you can also rigorously derive it as it's done in the appendix in the HAL book. Now let's look at some sensitivities. By the sensitivities, we just mean the partial derivatives. Now the delta shows the sensitivity of the call option price when the spot price of the underlying asset changes. So you hold now an option. You hold an option, and maybe now here over time, the spot price of the underlying asset changes. How much does the option price change? And we have seen that's actually a call shown by this so-called delta. It shows how sensitive the derivative price is when the underlying asset price changes. When you take this derivative of the solution, the Black-Scholes solution, you will get this. You will get the value of the cumulative normal distribution up to point D1. Now, it's not so easy to take this derivative. So let's take the derivative of this with regard to S. Naturally, you get ND1. And here S does not appear. So you could say, okay, that goes to 0. That doesn't matter, it's at 0. And so we just get the ND1. So you just get the ND1. But that's actually not true. If you do that, this argument is not true. That's too easy when you make that argument. You see the S is also here. So the S also influences D1 and the S influences D2, the price of the underlying share. So S matters here, yes, but it also matters here in the cumulative normal distribution. And so you really have to take here the derivative also of those cumulative normal distributions, and then you get the solution, the true solution. So it looks easy, but it's not so easy. You also have to take the derivative of that stuff here, and you have to do the complete derivative. Now, I don't do it. You can try it. I don't do it. I just give you here the results. So that's a so-called delta. We called it delta. It's a little bit of a funny name. So this delta here means the first derivative, the first partial derivative of the derivative security price of the option price with regard to change in the underlying share price. So this delta does not mean a change. So it's a bit unfortunate, this notation. Now the delta is not fixed. You can actually take the second derivative. So let's now take the derivative of the delta. So that's the second derivative of the option price. This is a delta is the derivative of the option price. Now let's now take the derivative of the delta, because the S is actually inside here of this D1. Okay, S appears inside here. I just showed it before. So the delta changes when S changes. You see, when S changes, the D1 will change. S appears here. So you can now take here the second derivative. It's just a derivative here of this cumulative normal distribution when D1 changes because S changes. And that's what you get. And that's positive. You see the cumulative normal distribution has a positive slope. S is naturally positive. Standard deviation is also positive. As a time interval, that's also a positive number. So we get here a positive number. Let's assume the cumulative normal distribution is always upward sloping. It could have flat portions, but let's assume it's just always upward sloping. So that's positive. This means that over time, the delta will change. It has actually to be adjusted continuously because changes in the stock price influence the delta. And this influence is measured by the so-called gamma. That's called the gamma. So when you write an option as a hedge fund, writes an option, then that and hedges it, buys the underlying shares to hedge it, there's a delta hedge. This delta hedge must be adjusted every day or even more. And that may not be possible during the financial crisis when the markets lock up. So there are here some residual risks that arise, particularly if you have a crisis. So then we have here the Vega. That's now the derivative of the option price with regard to changing in the scaling factor of the standard deviation of the geometric Brownian motion. Here's a sigma. That's what you will get. Again, you may try. Not so easy, but you may try. Do the derivative with regard to sigma. The sigma actually has influence here through the D1 and the D2. So when you do the derivative, okay, be aware, okay, the influence comes here through the D1 and the D2. It's not so easy to take it, but you may try. So when the underlying share becomes more volatile, then the value of the options on those shares increases. Again, that must be a positive number, because here I have just a share price, that's positive. There's a time interval, that's positive. And then let's assume that this is just always upward sloping, so cumulative normal distributions. We don't have a flat portion in it. Now, an increase in volatility makes it more likely that an option will be exercised. Maybe just by chance, because when its markets are more volatile, maybe just by chance it will be in the money when at the expiration date. And so the option becomes more valuable. So this will rise, so price of an option when you hold it. So actually, when you hold options and maybe financial markets become more volatile, then you make a profit. Your options, the price, the value of your options will increase. So maybe during the current crisis in financial markets, some people have made some money on this. So then the theta shows the change in the option price as time passes on, as small t moves toward big T. Now, the option will get cheaper. It's a negative number here. If you look at all the signs of the stuff here, okay, you will get a negative number. So moving closer to the expiration date, the value of a European call option falls. Again, you must do the partial derivative here of this solution here. Do the partial derivative now with regard to small t. Small t is up here, but it's then again also here and here. So also D1 and D2 will change. So it's quite a cumbersome partial derivative to do it. So as time passes on, the value of a call option, of a European call option, will fall. And then the row shows the effect of the interest rate on the value of the call option. When the interest rate rises, the value of call option will increase. And again, maybe during a financial crisis, when financial markets get tight, then the value holders of the call option make a profit here. Okay, so that's the story of today. That finishes today. Thank you.